Continuing on physical chemistry, chapter 2, we're beginning section 3 now. Now heat, the symbol for heat is Q. And it's going to be mc delta T. Now m is mass, C in this case is specific heat. That's what we should call it. Or we can call it specific heat capacity. And then of course delta means change and capital T is temperature. So m is mass, delta T is the change in temperature. So heat, remember, if it's absorbed by the system, is positive because that'll increase the energy inside the system. If heat is released by the system, it's going to be negative. Now Q1, released by the hot object, plus Q2, the energy absorbed by the cold object, is equal to 0. So whatever energy, heat, in a heat transfer, whatever heat is coming this way gets here. It doesn't just disappear or anything. So that's the law of conservation of energy. So if we have Q1 plus Q2 equals 0, then Q1 equals minus Q2, or Q2 equals minus Q1. And remember, Q is the symbol for heat. So we have the mass of object 1 times the heat capacity of object 1 times the change in temperature of object 1, and that's equal to minus the mass of object 2 times the heat capacity, or the specific heat of object 2, times the change in temperature of object 2. Now you notice though, the final temperature is going to be the same for both if you let it get to equilibrium. So both objects are going to have the same final temperature when they get to equilibrium. But we could have different initial temperatures. We could have this object starting at one temperature and this object starting at a different temperature. Now the units for Q is a type of energy transfer, so it's in calories or joules. Now C, the specific heat, it could be in calories per grams degrees Celsius, or calories per gram per Kelvin, or joules per gram per degree Celsius, or joules per gram per Kelvin. Now remember, the temperature, it can be in degrees Celsius or in kelvins. We're not really going to do Fahrenheit or anything else in this class. Now remember, the specific heat, we're going to say that's also a function of temperature and pressure. Now of course it's material specific too. And this, I didn't show it very well, but this is supposed to be a lowercase c. Now for water, H2O, the specific heat is about 1 calorie per degree Celsius, or 4.18 joules per gram per degree Celsius. Now, we can do this in a specific way, such as at constant pressure. So we have the differential of heat, so that's how fast heat is being transferred, or the infinitesimal change in heat at this constant pressure, is equal to mass times the specific heat at constant pressure times the differential of T. We're using differential instead of delta now because we're talking about the instantaneous change. So if we integrate both sides, we get the integral of the differential of heat at constant pressure is equal to the integral from temperature 1 to temperature 2 of mass times the specific heat at constant pressure with respect to temperature. Now the integral of a differential, of course, is just the original. So that means that the heat exchange, the heat flowed, whatever you want to call it, at constant pressure, mass is constant, so we pull that out and say mass times the integral from temperature 1 to temperature 2 of the specific heat at constant pressure, but as a function of temperature with respect to temperature. Now, lowercase c subscript capital P means the heat capacity at constant pressure. But remember, this is only going to be relevant if you have a closed system, you're at constant pressure. Obviously mass is constant, and this number is always positive. Now, if the heat capacity at constant pressure is constant with temperature, then we can evaluate that integral easily enough. We can say the heat flow, the heat constant pressure is equal to mass. We could pull this out of the integral. The heat capacity at constant pressure is equal to the integral from temperature 1 to temperature 2 with respect to temperature, which would be just T2 minus T1, or the change in temperature. Now remember, mass times the heat capacity at constant pressure, this is lowercase c, is equal to the total heat capacity, but this is uppercase c. So and then that's the heat capacity. This is a key property of the overall system. This would be, the lowercase c would be like for a certain amount of substance is intensive. This is the extensive version. So heat capacity at constant pressure for object 1 plus the heat flow at constant pressure for object 2 is going to be equal to 0, because whatever is flowing into object 1 is flowing out of object 2, or vice versa. So this is the heat flow at constant pressure. So we evaluate both of those. We get mass 1 times the integral from temperature 1 to temperature 2 of the heat capacity of object 1 as a function of temperature with respect to temperature is equal to minus mass 2 times the integral from state 1 or temperature 1 to temperature 2 of the heat capacity of object 2 as a function of temperature with respect to time. And remember, if they had different initial temperatures, this could be T1 prime. I didn't really show that there. I could do that. So mass 1 times the integral from temperature 1 to the final temperature. Remember, we said they both have the same final temperature. That's why we use T2 here. So the integral from temperature 1 to the final temperature of the heat capacity of system 1 as a function of temperature with respect to temperature. So to do the minus, get rid of the minus sign, we can just flip this integral upside down. So we have mass 2 times the integral from the final temperature to temperature 2. This means the initial temperature object 2 now. We sort of changed the nomenclature on you. So this is then the heat capacity of object 2 at constant pressure as a function of temperature with respect to temperature. So this is a key equation if you're going to be doing problems with a hot object and a cold object. And it doesn't even matter which one is one as long as you keep it all straight. Now it is important though, heat, it doesn't necessarily just flow through matter. We can actually say that energy can transfer without contact. We call that radiation. You know, kind of like infrared radiation and so on. You could argue it's not really heat, but it's kind of, it works the same as heat. So let's talk about work reversible and work irreversible, or there's also heat reversible and heat irreversible. Now let's say that we have an object A and an object B, and heat is flowing from object A to object B. Then we can say for a fact that the temperature of object A is higher than the temperature of object B, because I already mentioned before, temperature tells us the direction of spontaneous energy flow. So if the energy is flowing from here to there, in the form of heat or whatever, this temperature is higher than that. So you already know that the heat is going to flow from the hotter object to the colder object until they reach equilibrium, which means they're going to have the same temperature. Now Q is irreversible until temperatures are in equilibrium. So let's talk about the Zeroth Law of Thermodynamics. Let's say we have three objects, A, B, and C. If A is in equilibrium with C, and B is in equilibrium with C, then we can say for a fact that A is also in equilibrium with B. So that is all we're doing for Chapter 2, Section 3.